The last speaker for the session is Sushant. Vijayan. He'll be presenting some results in fixed budget in the best arm.
Thanks. So this is the third talk on bandits. So I think people are already familiar with what a bandit is. K distributions, each of them called as arms. At any time, T, an agent can pull one arm and sample from that arm. It will forego the sample from the other arm. And typical goals are regret minimization, identifying the best arm, trying to minimize the simple regret. These are the standard sort of goals in this region. So I'll speak a little bit about best arm identification problem, particularly the fixed budget variant. So yesterday, Anirban spoke about the fixed confidence regime, where the goal is to identify the arm with the highest expected mean by sequentially sampling the arms. That's called as a fixed confidence. Today, we will focus on the fixed budget, where you're given a budget of, say, T samples, and your goal is to minimize the error probability of declaring the best arm. So, as mentioned in yesterday's talk, Kaufman's work in 2016 showed that there exists an asymptotically optimal algorithm for certain classes of bandit classes, where asymptotically, as the confidence parameter goes down to 0, you achieve the optimal sample complexity. The question was, in the fixed budget setting, can we have a similarly asymptotically optimal algorithm? So we defined what's the answer? So you have an optimal algorithm pi star. It has the smallest sample complexity, which is the expected stopping time. And you divide by the log 1 by delta, because that's the correct scaling given by large deviations. Okay. So in the fixed budget setting, the same paper, Kaufman and Guerreria's paper, they defined the notion of asymptotic optimality using error exponents. So you define for a bandit class, the optimal algorithm pi star to be the one which attains the highest exponent for each bandit instance within that class. So there has been a long line of work. So starting with some frequentist lower bounds given by Audibert, they first proposed this successive elimination algorithm there. Gabrielian had an algorithm where they were trying to estimate the gaps between the arms, and they were trying to come up with algorithms which work for both fixed confidence and fixed budget setting. Carmen showed that successive halving was also good enough to achieve the same exponent as the first work of Audibert and Bobek. There has been a lot of work on minimax optimality recently. Some Japanese folks and have been working on this. There has also been work by Komiyama and Honda and the minimax optimality in the exponent sense. There has been some recent work on Bayesian fixed budgets, where you put a prior on the set of bandit instances and try to minimize the expected probability of error. There has been some work, a pretty old work, where they characterize very interesting classical static strategies. And finally, in July of this year, there has been a very closely related work which has come out in Cold 3 weeks back, which is Degenne's work. So generally, this problem has evoked a considerable interest in the bandit community, and was also discussed as an open problem in Cold 2022. So our first result is to show a general roadmap to show that there does not exist such an optimal algorithm for the fixed budget setting. The key idea, again, is a type 1, type 2 trade-off in this hypothesis testing problem, in spite of having adaptive sampling strategies. This is possible because of a Hofting bound type result presented in Hayashi. This is a reference which Ishan had mentioned in his previous talk. So what is the roadmap? We will try to show the impossibility by forming a contradiction. We will assume an optimal algorithm exists. it is constrained by certain information theoretic upper bounds given by Kaufman. We will show that various static strategies force this upper bound to be tight. Then Hayashi's Hofting bound type result will ensure that if you did achieve these optimal exponents in one hypothesis class, necessarily in the other hypothesis class, the exponents have to be smaller, strictly smaller. Therefore, you achieve a contradiction. We will show this explicitly in the class of two-arm Laplacian bandits. So we'll start off with the first step. The first step is an information theoretic upper bound. So this upper bound is created by a data processing inequality. What you do is you consider the Kullback-Leibler divergence of samples, and you apply data processing of Kullback-Leibler to get this quantity. Unfortunately, for a long time, this particular version of the upper bound was conjectured, but one can only show this thing if you can make a stronger assumption on uniform consistency. So by the way, we are searching for the optimal algorithm in the class of consistent algorithms. Consistent means that for a given bandit class, when you run this algorithm, it lets the probability of error go to 0 for all instances. So uniformly consistent means that there exists a particular, let's say, a horizon for every given epsilon, which controls the probability of error uniformly across this class. If you have this uniformly consistent assumption, then you can show a stronger bound. This uniformly consistent algorithm is true if the bandit class is finite.
So just define again the uniformly consistent.
So a uniformly consistent strategy is such that for any given epsilon, there exists an n0 such that the probability of error for any instance is less than this epsilon for all n greater than this n0.
And this epsilon and n0 are independent of probability instance?
Yeah, they are independent. That's a critical point. They're independent of the instance.
So if such a thing exists.
If such a thing exists for finite bandit classes.
So when you don't know the bandit class, it's one of those finite.
Yeah. So this is the upper bound on this error exponent. We will use certain facts about the Laplace family. So what is the Laplacian two-arm bandit? We are considering densities of the form of this particular form. So the previous, this upper bound, we will term it as upper bound of this instance. So we call this as mu. And for this particular class, you can derive this closed form expression for this upper bound. We will also assume, not assume, we are also given that the Renyi divergence for these two. U nu is this exponent. Yeah, this exponent here.
You get a closed form expression.
Yeah, we get a closed form expression for the Laplacian bandits. Okay. So now we need certain regularity conditions for Hayashi's Hofting bound. We'll extend the Hofting bound a little bit for composite hypothesis. Basically the basic assumption is that the Renyi divergence has to be twice continuously differentiable. Some of the salient properties of the Laplace family which allows this contradiction to work is that the Laplace family is not log convex. So if you take the log of the densities, they do not form a convex family. It's also not part of the exponential family because you're varying the location parameter. And another interesting point of the Laplace family is that if you consider all densities such that the mean absolute deviation is upper bounded by 1, then it turns out that the Laplace distribution is the one which maximizes the differential entropy. So we will use all these facts to arrive at showing the tightness of the upper bound.
So what happens to the Gaussian family? Is it still open or?
So for the two-arm Gaussian family, you always have a static algorithm which just gives half and half if the variance is known. If the variance is unknown, it is open right now. But if you have the set of arms to be large enough, if it is k, then the recent work of Vijayan shows that such an optimal algorithm is impossible.
So if you want to get two-arm Laplace algorithm, what are you going to do?
I'm going to conclude that there does not exist an optimal fixed budget algorithm for this class of Laplacian bandits.
And optimal is defined as the maximum or minimax?
Optimum is defined as achieving the highest exponents. It cannot be dominated in the exponent sense. So the pi star is the optimal algorithm. For the exponent it achieves in each bandit is as large as possible amongst the class of consistent algorithms.
So consistent algorithms with two arm Laplace distribution, the parameters can vary.
Yes.
And
it can be arbitrarily closed. The arms can become arbitrarily closed.
you can't have an adaptive policy which is going to dominate an exponent or the.
Yes. So, the class of static strategies we will consider is slightly constructed, but this is basically using the idea that you sample both the arms according to weights W and 1 minus W. Then, at the time when you have to make the decision, you consider the following two conditions if they are satisfied. That is the sample mean average deviation if it is less than 1. And if this particular inequality is true, then you declare the best arm to be the best empirical arm to be the best arm. Otherwise, you declare a predefined arm as best. Okay. So this strange looking static, it is static because the sampling proportions are prefixed. There is no adaptivity, there is no use of feedback there. Right? So the claim is that this previous family of algorithms are consistent. We have to show consistency. So it's a simple sketch. You use the fact that you are giving positive samples to a positive fraction to both the arms. So the means converge by LLM. Then the first condition becomes an equality. The second condition holds almost surely for all rational numbers. But because in this event, mu1 and mu2 have converged to the actual means, this function this double star condition as a function of B is continuous. So therefore, this inequality holds almost surely for all B. So that is enough to guarantee consistency of this class of static algorithms. What about, we have to now characterize the error exponent here. So we will use a version of Sanghavi's theorem for bandits. So the Sanghavi's theorem for this particular static strategy states that for any set B, the probability, the logarithm of the probability is the infimizer of these weighted KLs. So the W1 hat is the empirical distribution of the first arm, and W2 hat is the empirical distribution of the second arm. So suppose we consider a bandit instance. We are looking at, say, the unknown bandit instance that we have is one where A1 is greater than A2. So that is the first arm is the best arm. Then suppose you consider a static algorithm whose predefined declaration was 1 and the weights were W and 1 minus W. So the predefined declaration means when these two conditions, when this first case is false, what is the arm which you are outputting? So that is the predefined declared arm. If you declare that as 1, then the error event is basically going to be the following exponent here. So what you do is, what is this error exponent? It's basically saying, first consider if the first sample mean is x1 and consider if the second sample mean is x2. Then you infimize first on this set bx1, where bx1 is precisely this set where, okay, the mean is exactly x1 and condition star and double star hold. So what happens is, the reason why star and double star have been used is precisely because this infimization over this set, okay, so this particular set is exactly the Laplace distribution at x. It has been constructed that way. So the error exponent then becomes the following. This is basically an objective which is concave in W and convex in x1 and x2. So now, because W was arbitrary, you could now supremize over W. And because my optimal pi star algorithm must compete with even this static consistent algorithm, it must at least do better than this static algorithm in any instance. Now, it is straightforward to see that you can restrict x1 and x2 to be a one-dimensional optimization, and that x is going to lie between a1 and a2. So then you can invoke the minimax theorem and interchange the infimization and the maximization, and the quantity that you have here is exactly the upper bound which you had seen here. So this shows that the upper bound that Guerrier and Kaufman derived is tight for this class of bandits. So, okay, so the upper bound is tight in this case. So now you can verify that the Rene divergence is zero differentiable and all those regularity conditions that you require. Now I will state a slightly generalized version of hierarchy opting result. So what it is saying is that suppose you had an algorithm pi which is attaining an exponent of e power nu prime, where nu prime is in the alternate hypothesis of nu. Then necessarily the upper bound on the exponent is the following. Okay. Now you can see that this, as e nu prime is increasing, this upper bound is decreasing. So in particular, this quantity which I define as UH nu is strictly less than U nu, which is the original upper bound. So now all it remains to do is to substitute it into these bounds and derive the contradiction. And okay, so for a certain choices of A1 and A2, I can show that U nu is at least this much, and the opting bound is at most this much. Thereby, you have shown that there is a contradiction here. That means for this particular class, you cannot have a optimal algorithm. Existence of an optimal algorithm cannot exist. Now, some generalizations are possible. Because for the finite bandit classes, any consistent algorithm is uniformly consistent. This already shows that there cannot exist an optimal algorithm for finite bandit classes. Again, there are certain restrictions on this technique. So the quantity UH nu and U nu, they are exactly equivalent when the classes are log convex. This is a result of log, which we are utilizing here. The other issue is that it is restricted to 2 arms because we had to invoke the minimax theorem. And the reason why it worked for 2 arms is because the alternate set typically is convex in 2 arms. But when you have multiple, more than 2 arms, it becomes a union of convex sets which is not convex itself. Okay, so how does this compare with the recent result of Degenne? Degenne showed it that the impossibility of a fixed budget optimal algorithm for 2 arm Bernoulli and for Gaussian bandits with sufficient number of arms. But his techniques are restricted to exponential family. The current works technique is necessarily outside the exponential family because the exponential family is log convex. So in that sense, both the works complement each other. So if you cannot have a frequentist fixed budget optimal algorithm, then what is the other objective one might consider in the fixed budget setting? So we consider what is called a Bayesian fixed budget. You put a prior on the class of bandits, and you try to minimize the average probability of error. So there is no issue of non-existence of an optimal algorithm because that is guaranteed by dynamic programming. So for every horizon, you take a dynamic programming solution, a sequence of these things would achieve the optimal Bayesian exponent. One issue is typically in the general bandit literature, you assume that the means of the bandit arms can typically come arbitrarily close. But that would make the Bayesian exponent necessarily zero because the worst case arms, worst case instances will dominate the Bayesian average. And so therefore the exponent will be zero. So instead, what we'll assume to make this problem non-trivial is we'll assume a certain statistical gap. We'll define what is the statistical gap in the next slide. But this statistical gap ensures that there is a non-trivial positive optimal Bayesian exponent in existence. So why do we need to go beyond the DP solution? Because the DP solution is very hard to compute typically and doesn't give real insight into what is happening. Okay, so what is the formal notion of optimality here? It's basically the Bayesian exponent that I'm interested in. And that is guaranteed to be strictly positive under this notion of statistical gap.
What is mu here? This is the
DM, so M is the prior measure on the, yeah, it's a set of bandits. So we are interested in algorithms that maximize this Bayesian exponent.
So when you have a prior, then presumably it's most blowing up the probability of error is means coming very close.
Exactly.
So how are we handling that?
So I'm assuming it away by taking the statistical gap.
You're assuming that
There is at least a small positive gap.
no gap.
No, need not be no. Just has to be something positive. Okay, so so we will start on with some information theoretic ideas. So we use so the first point to note is that earlier in the frequentist setting, the best arm was just an unknown quantity, but in the Bayesian setting, it becomes a random variable. Okay, so then I can apply Fanos inequality to get a lower bound on the probability of error, the Bayesian probability of error. So one property of the Bayesian probability of error is that at the final step, when you are declaring the best arm, the optimal rule is always to take the map rule, which is the maximum a posteriori. You declare the arm with the best maximum a posteriori probability of being the best arm. So you have Fanos here. There is a nice reverse Fanos for these kind of map rules, which was derived by Ho and Verdun, which shows the opposite inequality. It makes sense because there's a close relationship between the uncertainty in the the best arm random variable and the probability of making an error when you declare the best arm. So this shows that entropy and the Bayesian error probability are bound together. But the interesting thing is when you're minimizing entropy, there exists a natural greedy optimal strategy, which is basically information gain. At each step of the algorithm, you have a posterior which is evolving. Now, at time t, you pull the next arm, which minimizes in expectation the posterior entropy of the best arm. So that is the notion of information gain. It is basically at each step, it is greedily maximizing the information between the next sample and the current and the best arm random variable. Yeah. So very quickly, a few lines of algebra will then show that the optimal Bayesian exponent is also achieved by the information gain algorithm because of upper and lower bounds given by Fano and reverse Fano. Okay, so there have been studies of minimax.
Is it equal to, yeah, are they equal to the assumption that you made that they're positive?
Oh, you mean the exponent?
Yeah. Probably, right?
Probably, probably. So, okay. So the minimax exponents have been studied in two settings. One in Komiyama, where they were interested in this. Okay, so one was trying to find out, trying to maximize the worst case exponent in a bandit class. They had proposed only a theoretical tracking algorithm that was extremely prohibitive computationally, and they then were forced to use approximate this tracking using a neural network. So they didn't propose anything which was fairly intuitive. The other thing was in information theory, there was literature on control sensing of hypothesis testing, where they studied the opposite, where you would take the maximum worst probability of error for each horizon and then study its exponent. So generally, the minimax exponents, upper bound and lower bound Bayesian error exponent. But in the case where the bandit classes are finite, they are equal. So naturally, you get that the information gain is minimax optimal in the exponent sense for finite bandit classes. So in some sense, you are actually solving two problems which are not solved in the but for the finite bandit class.
This is a new result.
Yes.
Okay.
Yeah. Okay. So the summary of the work is that we have shown that there cannot exist a optimal frequentist fixed budget algorithm. We used Fano and reverse Fano to show the optimality of information gain. And further work is typically to try and understand the nature of the information gain algorithm. We would like to characterize the exponent being achieved by this information gain. But it is typically a hard problem because it entails trying to understand the large deviation of a Markov chain with a discontinuous kernel. Again, making frequentist bounds for information gain, again, is probably a difficult thing to do, but there are certain structures which one might hope to take advantage of. So, I guess that's all. Thank you. We have
The next one will start. This is movie which you had to get.